Okay, last one. So here we can see we got another rational, which is nice. But look at this. The degree in the numerator is greater than the degree in the denominator. What kind of asymptote are we getting out of that? And it's 1 degree greater. You're going to get a slant, right? Let's do the vertical asymptote because that's nice and easy. We set that denominator equal to 0 and you get y is equal to a -1/2 because that's obvious. But with your slant asymptote and the fact that I have a coefficient in front of my 2 here, you have to do long division. So I've got 2x minus 1, plus 1, dividing into x squared plus 0x plus 12. You want to put that placeholder in there just to make it easier. Now you say, okay, you're looking at your first terms. I have x squared divided by 2x. Sometimes I like to come to the side and write x squared divided by 2x. And then literally, that's going to give you x over 2, which is the same thing as that 1/2 x, right? So then I'm going to multiply this by a 1/2 x. You take that and distribute it. So I've got 1/2 x times 2x is going to give me that x squared. 1/2 x times 1 is a 1/2 x. And that's why we line it up. You always line your x's up, your x squareds up, remember? It's probably been a while since you've done one of these, but that's okay. 0 minus 1/2 x is going to give me a -1/2 x. Drop down that positive 12. Then you do it again. I've got a -1/2 x divided by a 2x. So we know the x's cancel. And you've got -1/2 times, when you multiply by the reciprocal of 1/2, so you get a -1/4. And distribute that. -1/2 and -1/4 is going to be a -1/2 x minus a 1/4. And remember, when you do your slant asymptote, you're not concerned about what this remainder is here. It doesn't matter. The only thing you are concerned about is just having this y equals here with this slope and the y-intercept. I'm going to go back to blue. So for my slant asymptote, I've got y is equal to this 1/2 x minus 1/4. So we've got 2 of those there. All right, let's graph our asymptotes because that helps drive our function. So my vertical asymptote is at -1/2. So it's going right through there. My slant asymptote, yeah, these are kind of wonky donkey, but we can handle it. My y-intercept is a -1/4. So it's about right there. And then you're just doing up 1 from there and then over 2 because that's a slope. So you're just going to hit it right there. Then up 1 over 2. And then up 1 over 2 hits that. Up 1 over 2. Up 1 over 2. Up 1 over 2. I like to fill up my graph. Down 1, back 2. Down 1, back 2. Especially on these because then that helps drive your function. Okay. Slant asymptote, vertical asymptote, no problem. Now let's do some derivative tests. Still rational. So let's do our first derivative test. First derivative test tells me to take the first derivative. So the derivative of the top is going to be 2x times the bottom minus the top, 12, times the derivative of the bottom, which is a 2, all over the denominator squared. Okay, I'm going to scoot this up a little bit. Distribute that. F prime of x is now equal to a 4x squared plus 2x. I'm going to distribute a -2. So I've got a -2x squared minus 24 all over my denominator squared. 2x squared plus 2x minus 24 over that 2x plus 1 squared. Well, that top can be factored out a little bit there, can it? If I factor out a 2, what does that leave me with? X squared plus x minus 12. over 2x plus 1 squared. Oh, I could factor that some more. Well, that makes it handy. So I've got 2 times x and an x, a minus in the back, so I know my signs are different. I want a positive 4 and a negative 3, because that makes that positive 1, right? 2x plus 1 squared. So just our factoring. Now, when we're looking at this, we have critical values. Your critical values come from where your denominator is not as undefined. I guess we'll stay black. So if I want to find critical values, I'm going to say where x is equal to a negative 1/2, because that part is undefined. And you set your numerator equal to 0. So your numerator setting that equal to 0 has a possibility, well, does have horizontal tangents. The question is, does it flatten out as a horizontal tangent, or is it a maximum or minimum? That's what I need to know. So, my numerator, setting that equal to 0, will yield a negative 4 and a positive 3. This is horizontal tangent. All right, so my slope is equal to 0 there. Could be a maximum or minimum. Could flatten out my graph. I don't know. Let's come over here and do it. So we have our interval. I've got my first derivative is either positive or negative, and then that's going to tell me increasing or decreasing. So I'm going to scoot this over just a tad. So now I'm going to go, from negative infinity, what's the smallest number? Negative 4. Negative 4 to a negative 1/2. A negative 1/2 to a 3. And a 3 to infinity. Let's do it. So I'm going to look at my first derivative and some value in there, which is going to go with a negative 5 just because it's easy. Again, this is always positive, and this is squared in the denominator, so that's always going to be positive too. I can't come up with anything else there. So what I'm really looking for is, do I have anything negative? This is going to be a negative 5, making that negative, and negative and a negative is more negative. So positive over positive, I know my graph is increasing, because negative times a negative up here is a positive. All right, so f prime of negative 1, because it's the smallest number I can pull off there. So a negative 1 there is going to make this positive, negative and more negative. So a positive times a negative is a negative. So this is decreasing. All right, so, here we finally get 0. That's nice. Let's plug in a 0. So 4 and a negative. That's also going to give me decreasing, right? A negative over a positive. And if I look at the number 4, that's a positive and that's a positive. So we're just dealing in terms of positive there, people. So this one is increasing. Now here's my question. What do we know from the very beginning? Yes, my vertical asymptote. So we're focusing right there on that vertical asymptote. I know without a shadow of a doubt that's automatically a vertical asymptote. Those other two yahoos, that's where we can do some work on it. If I'm going to increase to decrease, I have a max. If I'm going to decrease to increase, I have a minimum, right? So just keep that in mind. X squared plus 12 over 2x plus 1. Since I can't see my whole page at once, and you can see it too. Otherwise, it gets way too small. I'm looking here at a maximum at x is equal to negative 4. So we plug that in. F, original function style. Anytime we find our points, it goes back into the original function. So we have negative 4 squared plus 12 over 2 times negative 4 plus 1. So f of negative 4 here is going to be 16 plus 12 over negative 8 plus 1. And that's going to give me 28 over negative 7. So f of negative 4 is negative 4. That's a maximum. All right, let's see what's happening at our minimum. It's happening here at x equals 3. Plug it in. F of 3 is 3 squared plus 12 over 2 times 3 plus 1. 9 plus 12 in the numerator is a 21. 6 plus 1 is 7. So f of 3 is 3. Oh, crazy. Check that out. That's our minimum. 2 points. Let's put it on our graph. I know that I have a maximum here of negative 4, negative 4. Negative 4, negative 4. Okay. 1, 2, 3, 4. 1, 2, 3, 4. And we know that that is a maximum. So that has to be like this, right? And a minimum is at 3, 3. 1, 2, 3, 1, 2, 3. So this has to be a minimum. All right. Now I'm out of room on this page, but we are going to do our second derivative. So whenever we go through here and we find our second derivative of this lineup, where are we going to focus? Or down here at the very bottom? No. We're going to look at this middle step right here, because I've got a polynomial on the top, which is easy to take a derivative of. I don't have to go through and try to do any kind of product rule or mess with anything like that. So I'm going to look at this step right here, and I'm going to take this down here for my second derivative. I'm going to take it to the next page here. So I actually have a second derivative test. So with our second derivative test, I'm going to write the first derivative here just so we don't lose it. 2x squared plus 2x minus 24 over this 2x plus 1 squared. Okay. So the derivative of the top times the bottom minus the top times the derivative of the bottom, which is a 2 in front. And then keep, oh no, come back here, little fella. Keep the guts times the derivative of the inside all over the denominator squared. Now again, notice what happened, right? I've got a group of that 2x plus 1. So we can factor that out and simplify better. So if I factor out a 2x plus 1, that leaves me with 4x plus 2 times still a 2x plus 1 left over minus 4 times this 2x squared plus 2x minus 24 all over this 2x plus 1 to the 4th. And I can break that down. One of those takes out one of those, just leaving me with 3. All right. Let's multiply this out. My second derivative is going to be an 8x squared plus 4x plus 2 minus, if I distribute that, an 8x squared minus 8x plus, oh my, what's 4 times 24? 96. Check my math. I think that's right. Yeah, I think that's right. Okay, now let's cancel out what we've got. There's a positive 8x squared and negative 8x squared. Ooh, plus 8x minus 8x. Oh, that's sweet. The only thing we're adding is 2 and 96. Wow, that worked out, didn't it? So my second derivative is 98 over 2x plus 1 cubed. So what's a critical value then? Yeah, just a negative 1/2 right there at my asymptote. Cool. I don't have to worry about that numerator. So let's make our chart. We've got an interval. I want to know where my second derivative is either positive or negative, and that's going to tell me if it's concave up or down. I'm going from negative infinity to a negative 1/2 and a negative 1/2 to infinity. Okay, so I've got a second derivative here. Oh, negative 1's probably the easiest, don't you think? So my numerator is positive no matter what. If I plug in a negative 1 here, that's going to make this negative, and it's an odd power. So that's a negative. So I know that this is concave down. All right. So if I take my, let's go with 0. Why would not? If I plug in a 0, we know it's always positive on top. And if I'm plugging a 0 in here, 1 cubed is also positive. And that one is concave up. And in between there is that vertical asymptote. So I don't have any inflection points, but I'm concave down to concave up, right? All right. So up to that vertical asymptote, it's concave down, meaning concave down, right? Up to my vertical asymptote. Then after my vertical asymptote, I'm concave up. Let's see how that looks in my problem. Is this concave down? Is this concave up? Pretty sweet, right? And we can also look at this and say, yes, this is going concave down. That circles up. Don't make that pointy. That's a bad graph. Let me do it again. Oh, 1, 2, 3, 4, 1, 2, 3, 4. So we know that this is still smooth and continuous here that we're looking at. That's concave down. And my graph also tells me I'm increasing to decreasing. So it's not a high increase, but it is still increasing to decreasing, right? And it's concave down. Check. Over here, my graph goes up like this. It's concave up. I am decreasing to increasing, so decreasing to increasing. And I've nailed it. Graphed 2 points. 2 points, that's it. And you can get that whole graph. Take a look. Practice this graphing. It's so important that you know these features of a graph. The first and second derivative test, you have to write these charts in here because they tell you so much more than just max and min. If you only have max and min, I'm not taking that. You got to tell me everything I need to know about that first and second derivative. All right, great job, guys. Go practice.